In this video, I'm just going to give you kind of a general overview of what some different polynomials look like. So we'll just start with the easy ones and we'll go up. So we'll start with a constant function. Sorry, degree. A constant function has degree 0. So an example of a constant function would be f at x equals some number. So I'll say f at x equals, let's go with 2. It could be any number. It could be pi. Any real number. So what does a graph of that look like? Good old crooked y-axis. So I'm not going to spend a lot of time on this because you should know what this looks like. You would have learned, I guess, in grade 9. So this is a horizontal line going through the value y equals 2. I guess I could do a solid line. So this would be the function f at x equals 2. Notice the domain is all real numbers. This line keeps going forever in both the positive and negative directions. The range of this function, so the range, that would just be which y values does it take on. So it only takes on the one y value, 2. So the range of this function would be just the set of the number 2. So you could just write it like that, or if you want, you could write it, suppose you could write it like this, all y such that y is equal to 2. It's a little longer way to write it, but they're both good. So that's a constant function. Not too much, not too complicated, don't have to spend too much time on that. The next one we're going to look at is a linear function. So again, you should be fairly familiar with these from grade 9, I guess. So a linear function would be one of degree n equals 1. So an example of this is just a line. So you've been familiar with the form y equals mx plus b. We're going to use f at x instead of y, but any function like this. So let's say 2x plus 1. So the degree here is 1 because the highest power is 1. 2 would be our leading coefficient, so because it's the coefficient of the term with the highest power. And you know from grade 9 how important it is to know what that coefficient is, right? That's the slope. It tells you a lot about the graph. It tells you sort of if it goes up or down, or increases or decreases. It tells you, how fast this happens. So that the leading coefficient is very important in a linear function, right? It tells us the slope. So we know what this one looks like, right? It's oh, sorry, wrong point. The y-intercept is 1. And I'm not even really going to bother worrying too much about what the slope looks like. I'm just going to assume that the x scale is appropriate to make that a slope of 2. So this is the function f at x equals 2x plus 1. So again, notice domain is everything. Talk about the range again. So the range of this one is all the y values it takes on. Well, notice this line, these arrows indicate that this keeps going up and up and up and up. So you're going to keep going up and cover all the y values up here, and the line would keep going down. So it's going to cover all the y values down here. So this one, the range is a set of all y such that y is an element of real numbers. It's all numbers. Or you could also write it sometimes. We just say y is a real number. So that notation's okay too, if the set is all real numbers. Okay, so that's a linear function. Not new. Seen that many times before. Now we'll look at quadratic functions. Again, spent a lot of time on these, although you probably didn't call them quadratic. You didn't use the word functions in grade 10. But this is a degree of 2. So an example would be something like this. F at x equals, let's put a negative in front of the x squared term, plus 2x plus 1. So we know from, again, grade 10 that these functions are always going to be what we call parabolas, or the graph which matches this function is a parabola. Um, in this case, our leading coefficient is this number here. So the leading coefficient is 1, or sorry, negative 1, right? So negative 1, that's the number in front of the x squared. So you know again how important it was to know this in grade 10. What number is in front of the x squared? That determines sort of which way you open. It determines like how steeply you open. Is there a compression or a stretch? So it was very important to know this. I'll just quickly sketch a graph. So we know a negative leading coefficient means we're opening down. So this one's going to look something like this. I'm not going to bother like really going over how to graph the parabola right now. You should again know that from grade 10. The vertex here, I mean, it's not obvious, but the vertex for this one is, I believe it's 1, 2. Yeah. So the highest point on this one is 2. So I mean, you might be saying, how do you know that from just looking at this? Well, you'd have to either convert it to vertex form or find the vertex in one of the ways you know from grade 10. If you don't remember, I got a playlist on quadratics from grade 10, so you can go back and check one of those out. Or you can ask. Okay, so this is what this parabola is. Notice the range here. The range here is, it's not going to be all real numbers because there's a maximum value. In this case, there's a maximum value of 2. So this would be the set of all y such that y is less than or equal to 2. Right? We only deal with y values less than or equal to 2. If the parabola was opening up, then the range would be bigger than a certain value. But one thing to notice is that in quadratic functions, the range will not be all real numbers. It would only be, depending on whether it opens up or down, less than or bigger than a certain value. So those are quadratics, not new. Cubic functions. So cubic function. These are of degree. These are degree 3 polynomials. So degree 3, alright, n equals 3. What else have I been writing? Okay. So we'll start with an example. Well, actually, this one, I'm going to give you a couple of different examples because unlike linear and quadratics, cubic functions can sort of differ in the way they look. Right? Remember, a linear function was always a line, right? It changed, the slope or the y-intercept, that changes, but it's always a straight line. It's always that same shape. A quadratic was always a parabola. I mean, it can get skinnier or open wider or open, narrower, move up and down, flip up, flip up or flip down, but it's always that same basic shape of a parabola. With a cubic function, you can kind of have sort of different shapes. So remember, a cubic function generally looked like this: a x cubed plus b x squared plus cx plus d. But you're not always going to have all these terms. Like the base cubic that we usually start with, you usually are going to see, and I would guess you saw this last year. So you would have probably made a table of values. If you haven't, it might be a good idea to just do a table of values right now just to try to get see what the shape of that looks like. I'm just going to assume you've done it. If you haven't, pause the video, do it, and you'll see if you're right in a second. So the base one we look at is this one, x cubed. So you may be saying, well, x cubed doesn't look like that. What happened to all these terms? Well, all this means is that b was 0, c was 0, and d was 0, so these terms went away. It's still cubic as long as you have the x cubed term, and a would have been 1. So this one looks, oh, that's a terrible drawing. This one looks sort of like this. Okay. So that's one example of a cubic. Another example, when you throw in more terms, when the b and the c are not 0, it changes the shape of the graph a little bit. Here I'm going to put a negative x cubed plus, let's say, 2x plus 1. Notice I don't have the x cubed term, but I do have an x term. So just by doing that, actually this the graph I'm going to do might not match exactly this function, but I'm just going to try to give you an idea of what might happen. Well, one thing that's going to happen is, this for sure would happen. The negative leading coefficient is going to do something similar to what happened when you had a negative in front of a quadratic. It's going to flip this cubic upside down. So instead of going down here, we're going to be going up here. But what else happens, because there's more terms in the middle, you get sort of this thing where you go down and then up and then come back down, as opposed to this one, which was just sort of always going up. So you get kind of, it almost looks like humps. So that happens, like a cubic could look like this, or it could look like this. But notice that in both cases, the range is still the set of all real numbers. Right? We go up forever, and then we go down forever over here. Or up forever, down forever. So it covers all the y values. What am I at? My fifth example would be a quartic. So that would be one of degree n equals 4. And again, you can get different examples of functions. Usually the base one we start with is f at x equals x to the 4. So you don't have those other terms, you just have x to the 4. It's easy to start with. And again, if you haven't seen what this looks like, you might want to start with a table of values just to create it for yourself. But this one looks kind of similar to a parabola. The only difference is it's sort of flatter right here, and it goes up steeper. But it's still that same kind of U shape. Doesn't quite look like a parabola, but it looks a little bit different. But you could have other examples. So you could have ones like f at x equals, and you can put like 2x to the 4 plus 3x squared plus 5x minus 1. Right, so there could be more terms after the x to the 4, just as long as there is the x to the 4 term. That's the key. How can the graph change? I don't know exactly what the graph of this one looks like, but you're going to see things like, you could get ones doing things like this. So it'll go up like a parabola, but then it kind of goes back down, but then it'll go back up again. And then different modifications of this. Sometimes, the hump, actually, if it was a negative leading coefficient, you'd get that same situation of parabolas. So if there was a negative here, then it's going to flip this. So you could get something like this. So notice that like these kind of humps, it depends on the function. They might be at the same level. In this one they weren't. In this one they were. But for a quartic, you're going to get sort of these two humps, or you might even say 3, because there's one there, and one there. Okay, but again, notice the range is not all real numbers. I won't write well, actually, the range for this one I could write down. The range for this one was the set of all y such that y is bigger than or equal to 0. So in a quartic, you've got a max or a min, right? Here the min would have been here. Here there would have been a max here. So the range would be restricted to a set of the real numbers. It won't be all the real numbers, or a subset of the real numbers. Okay, and the next one, very quickly, I'm going to try to do a quintic. So this would be of degree 5. So your base quintic would be f at x equals x to the 5. This one kind of looks like a cubic, except it's a little flatter around here, and it goes up a little bit steeper. But again, that's kind of your base one. You throw in more terms, different things happen. This graph I'm going to do doesn't match this, but sort of generally what can happen with quintic functions. So the negative, that would make it open differently. So in a quintic, you're going to have something like this. So that would be like a cubic, but then you have one more hump than a cubic. And then it could be opening different ways. There could be, the humps are at different levels, But basically, that's what a quintic's going to look like.